Hi, welcome everyone. Welcome to this course of Introduction to Statistical Mechanics of Soft and Active Matter Systems. So, in the last two classes, we started the discussions about uh, Brownian motion, and we got to know about how this Brownian motion is different from a deterministic system, and we calculated different time correlation functions to see that indeed uh, to to actually observe or actually predict the motion of a particle suspended in a fluid, we need to add the random force to the equation of motion, which is called Langevin equation. Okay, so today we will restart our discussion from that part. Okay, so let me share my screen. Okay, so you can see my screen here. So we were talking about in the last class. We first tried to get the velocity correlation functions, and we see that if we talk about a certain variable xi, which is a you know a quantity of that system, physical quantity that we can study of that system, physical system, and if we define a derivative of that, then we can get the time correlation function of the velocity from the position and time correlation by this relation. And then we try to see that how Brownian motion of a free particle is can be predicted. So to do that, first thing we need to do is that when a particle is suspended in a fluid, there should be some Stokes drag, which is a resistive kind of force, and that Stokes drag is proportional to the velocity of the particle. If the velocity of the particle is more, drag amount will be more, right? So now to effect to get the equal sign from the proportionality, we have to introduce a proportionality constant. We got this proportionality constant, which happens to be the friction coefficient or drag coefficient, right? Now for a spherical particle of radius a, this stroke drag or friction coefficient, is 6 pi eta a, where a is the radius of the Stokes radius of the particle, eta is the viscosity of the fluid where this particle is suspended. Now for a macroscopic free particle, if we just take this Stokes drag, then the equation of motion should be written like this: m dvdt is equal to minus gamma v. Now if you solve it, these equations, you get this solution where velocity will be v naught, which is a constant which is coming from the initial condition, is v0 e to the power minus t by tau m, tau v is m by gamma, some time constant, and this time scale or this times constant is very less, which is around picosecond. And you can see that the velocity of the particle falls off exponentially after very rapidly it becomes zero. But that is not something that we observe in real systems. We can see that if you talk about a pollen grain or dust particle in a fluid, and if you observe them in under microscope, they are sort of fluctuating or they are moving, and you can see under the microscope. So what are we missing on in this assumption? So we are missing on we should take into account the fluctuation of the forces acting on the particle, which are coming from the collisions between the fluid molecules and this macroscopic particle. So now we remodel the equation of motion as mdvdt, and we have introduced a certain term which is a fluctuating force. Okay, and now we need to talk about when we have written this thing. So in this quantity we have accounted all the collision force that is coming from the constituting fluid molecules. Okay, and this equation is a Langevin equation, and this is a phenomenological equations, because here we do not keep track of each and every collisions, because you can see here we are replacing the information of each and every collision by some kind of a phenomenological term, the fluctuating force. Now we need to know about this fluctuating force, how these properties are, how is this fluctuating force behaving. So to do this, we need to get some statistical properties of this force. So now we will assume something, but that will be based on some logics. So first we will talk about the average of this random force, and then how these random forces, their time correlations behave. So it is very natural, quite natural to assume that this average of the random force is 0, because it is not giving you some drift or some velocity for a persistent time. That means it will be nullified, the forces will be averaged out to be 0 if we observe the particle for a long time, right? So if we take the average of this force to be 0, then that's a good assumption, right? Now second thing is how this random force is arising from this time correlations. So for that we have assumed that since these are collisions, these collisions are happening, so we should take a correlation time of this collision should be very less. This is around around the level of picosecond, because these collisions are happening very fast. So this collision time will be around the correlation time will be around the collision time, which is around picosecond. So now for our macroscopic time scale or our observation time scale, which is around millisecond, this we can assume to be a delta function, this correlation, because it's like the correlation dies instantaneously. Now if you assume these things, and this is a correlation constant, we will measure this correlation constant. So for that we have solved these Langevin equations to get these equations, and we got this Vt square average, and we have used the equipartition theorem to get this constant to be around, because this Vt square average is kBt by m. This is from the from our equipartition theorem, and from that we got this constant to be 2 gamma kBt. So from that we can easily write this time correlation of this random force to be taking this form. Okay, so now in this relation you can see that how the fluctuations of the forces in the left hand side, you can see the fluctuation of the forces, and the right hand side you can see this gamma term. So this is a famous, we can think of as, in the left hand side the fluctuation is there, in the right hand side some dissipation term is there. So this is called a fluctuation dissipation relations between between these two things, or in this system this is the fluctuation dissipation relation. Okay, now this time correlation function of random force is independent of particle of mass m, because here in this relation there is no mention of mass m, right? Now this time correlation function is, since it is independent of particle of mass m, that can be seen pretty easily. So it is quite logical that this random force determined by the fluid molecules alone, because there is no uh, uh, in this relation there is no mention of any property of the particle, right? So that is thing. So that is its statistical properties should be independent of the mass of the particle. So the random forces statistical property should be independent of the mass of the particle. Similarly, from average and time correlation functions, we can see that there are not, it is not sufficient to specify the statistical properties of the random force completely, because from average we can get the first moment, and from the time correlation functions we get the second moment. But for a complete specifications we have to make a further assumptions. Now random force, if you think about it, random force is sum of all these collision forces excited by many fluid molecules. Now if it is summation of all the forces, then its distribution should be Gaussian. This is coming from central limit theorem. Though what central limit theorem says is, if some variable, let's say x, so central limit, I will talk about this more in details, but I am just talking a little bit about this in this discussion so that you can get this. Let's say x is a random variable which takes value x1, x2, dot 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 xn. Now if it satisfy, and these variables, these random variables, they are independent, that means it does not depend, x2 does not depend on x1 and so on, they are independent, and but these random variables, they follow a certain distribution. It need not be Gaussian distribution, certain distribution. If that is the case, then given the n is large, if we take this variable which is summation over all these random variable, and this variable follows Gaussian distribution. So this variable follows Gaussian distributions. So that is quite easy to say that how it's done, but it's quite simple. We will talk about it in great details. Okay, so so first, so remember one thing, this variable, small x variable, these, they need not be following Gaussian distribution, they can follow exponential distribution or any other distributions. But if you take these variables or observation, if you take this observation for large enough time or large number of observation, if you take, and if you then take the summation of those variable, and then this summation of that variable will follow the Gaussian distribution. Okay, so if you take, let's say first time, if you take observations of 10,000 observation of some variable which is following a certain distribution, and if you take the summation of that then if you repeat that whole thing again 1,000 times, and if you plot the summation of those observations, then it will be always following a Gaussian distribution, which is famously called as bell curve. Okay, so if it is p of x, this is x, this follows this. So I will talk about it more detail when we will talk about the Fokker-Planck distributions and all these things, sorry, Fokker-Planck equation, all these things. So now today what we will do, we will resume our discussions from when we will calculate the Einstein's relation, the famous Einstein relation. Okay. So to calculate the Einstein relation, what we have to do, we have to first calculate the time correlation function of the particle velocity. So we need to first we need to calculate the time correlation of particle velocity which is nothing but Vt and V of t prime. So this is like time correlations of velocity at certain time and velocity at a different time. So we need to calculate this. Now for that we need to take some help from the previous equation. So we will take help from equation number 26, this equation, and equation number 22, these equations. Okay. So if you take these two thing, then so Vt is like this. So Vt is like this. So let me write it as, so Vt is 1 by m, and let me copy this. So this is Vt, and we will also take help from equation 26, which is Frt prime 2 gamma kbt delta t minus t prime. Now if it is Vt, then what will be this term? So let's say Vt and Vt prime. So first there will be 2 1 by m, so this will be 1 by m squared, and for the first Vt we will write integration of minus infinity to t, and the variable is written as dt1, and the for second variable Vt prime we will take integration variable from a minus infinity to t prime, which is dt2, right? Now for first term this was e to the power minus t1 by tau v, so this will be e to the power minus t minus t1 by tau v times, for this one, e to the power minus t minus t2 by tau v, and this is fr t1, sorry, t, and this should be fr t1, and this should be fr t2, and there this will be the average. So you understand this point. This and this Vt and Vt prime, first we will product this. So if you write this, this will be the product without this angular brackets, and if you take the average will be over this random force. Okay. Now what is this average? This is this term where t is replaced by t1 and t2 is will be replacing t prime. So if you write that, then that becomes 1 by m squared minus infinity to t dt1 minus infinity to t prime dt2 e to the power minus t minus t1 by tau v e to the power minus t minus t2 tau v, and this one will be 2 gamma kbt delta t1 minus t2. Okay. Okay. Now we need to do this integration. So let me write this equation number as 27. Okay. Now there can be two situations. So there may be two situations. So now we will do this integration. We will be doing this integration separately for two cases. What are those two cases? First case where t is larger than t prime or t is greater than t prime, and second thing is if t is less than t prime. Okay. So if you do that, so first thing it will be, so first thing, okay, so let's say first thing t greater than t prime. Now if t greater than t prime, then our these calculations become vt prime 1 by m square, okay, 1 by m square minus infinity to t dt1 dt1. So now we need to take this integration. So that integration becomes, if you take dt and this delta, then t prime is in between this. So from minus infinity to t in this line, t prime will be somewhere here, okay, t prime will be somewhere here. So now, sorry, this will be t prime, this will be t prime, okay. So now if you do this, then this becomes e to the power minus t minus t1 by tau v into e to the power minus t prime minus t2 by tau v 2 gamma kbt. So only thing which is doing here, so we are doing this part. Okay, so t1 becomes t2. Okay, so since t1 become t2, so t2 and t1 same thing, then this guy will be t1, this guy will be t1, right. Now if this is T1, then we can easily write next thing as 1 by m squared, 1 by m squared. We can take, since this is t and t prime is constant, we can take outside this one, and this becomes e to the power minus t plus t prime by tau v minus e to the power t dt1 e to the power 2t1 by tau v into 2 gamma kbt. Clear? This term clear? So this is t1 by tau v, from here to t1 by tau v, so this will be 2 t1 by tau v. Now if you take this integration, then it becomes 2 gamma kbt by m squared e to the power minus t plus t prime by tau v. Then here e to the power 2 t1 by tau v times 2 by tau v minus infinity to t. Clear? So from here you can easily see tau v. Okay. So for if t1 is minus infinity, so this will be 0. So only term will be 2t by tau v. So that makes 2 gamma kbt by m squared into tau v by 2 into e to the power minus t plus t prime by tau v times e to the power 2t by tau v. So now tau v, you know tau v is m by gamma. So if it is m by gamma, so 2 and 2 cancels out, and m by gamma, so gamma gamma cancels out and m by m cancels out, so it becomes gamma kbt by m square times m by gamma times, from here 1 minus t by tau v will be balanced by this, so this will be t minus t prime by tau v, t minus t prime by tau v. So from here you can easily write m 1 m cancels out, gamma gamma cancels out, so kbt by m e to the power t minus t prime tau v. So this is one relation. Remember, this is for when t is greater than tau prime, for this relation. Now second thing, when t prime greater than t, there we can write, now same thing here, we done this thing, there we will do this integration first. So for this relation, what I will write is, I will take from here, so vt prime. So first, since t prime is more, so I will write that thing first. So minus infinity to t prime dt2 e to the power minus t prime by t2 by tau v this side, and into 2 gamma kbt, since it is constant. The only thing is minus infinity to t dt1 e to the power minus t minus t1 by tau v into delta T1 minus T2. Now whenever there is a function and it's a delta function, so that variable will be replaced by this T2. That is a simple thing, right? So this only change will be this guy. Only change will be this guy. It will be only replaced, T1 will be replaced by T2. So for that, what I will do, so this is for this region, where this to this is minus infinity, this is T prime and T in between region. Okay. So for this, then it becomes 1 by m squared minus infinity T prime dt2 e to the power minus T prime minus T2 by tau v into 2 gamma kbt into e to the power minus T minus T1 by tau v. Now T1 will be replaced by T2, so this will be T2. See, similar kind of steps we are taking. Now since you just get this outside, so this will be 2 gamma kbt by m squared, and only integration remains e to the, sorry, so this T prime will be, T prime is, so this will be T prime probably. Did I mistake something? No. Okay, so this will be e to the power minus T plus T prime by tau v, and similarly e to the power minus T prime dt2 e to the power 2 T2 by dv. Same thing, same way, 2 gamma kbt m squared e to the power minus T plus T prime by tau v, and this chap will give you e to the power 2T2 by tau v divided by 2 by tau v, and minus infinity to T prime. So for minus infinity it will be 0, for T prime it will be there. So for this it becomes 2 gamma kbt by m squared into tau v by 2 into e to the power minus T plus T prime by tau v times e to the power 2 T prime by tau v, and that makes it kbt by m e to the power T prime minus T by tau v. So this is equation 28.2. Now if you see this expression and this expression, now how can you write it combinedly? To write it combinedly, you can totally write then, you can write then so whenever something is, we can totally write as Vt prime is equal to kbt by m e to the power minus mod of T minus T prime by tau v. This is equation 29. So from here, if T greater than T prime, this mod sign will be T minus T prime, mod sign will be there and mod sign will be taken out, and this will be T minus T prime. If T prime is greater than T, then it will be reverse, minus of T minus T prime, so minus and minus plus, so this will be T prime minus T. So combined you can write this. So the general prescription is, general prescription is general prescription is if t is greater than t prime, variable for t prime, which is t2 here, that integral should be calculated first, because this is because if you take if you do the if you want to do the integration of the delta function, there this variable needs to be, this t prime needs to be in between, right? So calculate it first, and if t greater than t prime greater than t, integral integration for variable of t, which in this case t1, should be calculated first. Okay, so this is the general thing. So now you get this, now you can easily get the mean square displacement from this. Now how to get the mean square displacement? So now if you see, also one thing you can see from the equation 29, what you can say that from equation 29, from equation 29 you can easily say that autocorrelation function, let me write it as autocorrelation function is an even function of time, that you have seen in equation number 13 also. So that part is done. Now equation number, now how mean square displacement will calculate? Now calculating mean square displacement from this relation. So what is mean square displacement? It is displacement and its square, and then you have to take the average. So what is displacement? Displacement is this one, xt minus x0, this is displacement. What is square of this? So this is its squared, then we need to take the average. So this is the mean square displacement. Now how to do that, take that is, then that can be calculated using this 202t dt1 02 t t1 greater than t1 d2 t d2 v of t2 and v of 0 its correlations. So you can see here also same thing. So this is actually same thing, right? If you want to get this so for if you replace j by I, so this will be the same thing, x by xit minus xi0. If you replace j by I, then it will be xi t xi0, then it's squared. This will be 2 xi dot, means the velocity of t2, and velocity of j, since we are replacing j by I, so this will be v of t2 and v of 0. So we are just using this relation. So we are using this relation only. Here same thing, since this is autocorrelation, right? So now in this way we can use the, now this part we have calculated just few minutes before, like we can get that thing easily. Okay, we can get that part easily. Now to get that, what we will do, is so first we will use certain assumptions. What are those assumptions? We will assume that velocity correlation time is negligibly small in the time scale under consideration where we are want to measure it. So we will say so what we will do is, also, so or we can easily calculate the whole thing. Just a minute. Yes. So what we will do, we will first take this relation, so we can calculate square displacement like this. So this is xt minus x0, and substitute it like this. So then 2 into 0 t dt1, 0 t1 dt2, and you write this relation kbt by m times e to the power minus t minus t prime by tau v. So let's say this is mod value. Now you want to calculate like this. Okay, so now how to do that? So there will be two steps. First, if t greater than t prime or t greater than t less than t prime, right? So since this is t and 0, since this is p and 0, or we can take a certain approximations. Okay. Think about it, how to do that. Okay, just for 1 minute. So okay, now if you think, so you can do the whole calculations like this. Now since this is t2, so it will be, you presumably written as like this, but it should be, there should be two region. Okay, one is greater than this or below that this. So now what we will do, we will use a good approximations. So what we will use here, so we will do that this velocity autocorrelation time, this time we consider the velocity autocorrelation time tau v is very negligibly small, negligibly small in the time scale of our observation. Okay, of our observations. That means tau v is very small than t. In that case, in that case, the characteristic value of T1 in this equation, let's say this equation is equation 30, T1 in equation 30 is much larger than tau v, is much larger than tau v. Therefore, you can easily approximate this integral to be like, so therefore the integral for T2 in equation 30 can be approximated as 0 to T1 dt2 v T2 v0 as 0 to infinity, because T1 is very large, right? 0 to infinity d2 v of T2 and v0. and therefore this right hand side, it's a constant and it is written as the right hand side is a constant and it is written as some constant d is equal to 0 to infinity dt v of t v of 0. Okay. Now from this above two equation 31 and 30, we can write, then if that part is done, then only thing remains is xt minus x0 whole square is equal to 2 0 to 0 to t dt1, and this part is d, so it becomes 2d mod of t for t very greater than tau v. So from here we can get the famous so this d is called this constant d is called self diffusion constant. Okay, now you can say that what is this self diffusion constant, right? What is this self diffusion constant? Because we have heard about the diffusion constant. Now here you can write that self diffusion constant is different from the usual diffusion constant which appears in the diffusion equation of particle concentration. Because so far in your college days you talked about diffusion coefficient for a concentration gradient, right? So this diffusion constant is a collective one. So the latter constant is a collective diffusion constant, and it actually agrees with the self diffusion constant in dilute solutions, in dilute solutions. So that is the main difference. So there is a difference between these two things. Okay, so now if you compare equation 29 and 32, equation 29 and 32, you can write, compare if we compare equation 29 and 32, 29 is this one and 32 is this one, then we can write a certain thing. How? Because there in Vt V0 relation you can get this part as, so then comparing D becomes kBt by m into tau v. How? How? Let me show this. This is 34, because your equation then becomes t becomes 0 to infinity dt, and Vt is this one. So this will be e to the power minus t by tau v. So kBt by m into e to the power minus t by tau v. Okay, t by tau v. So from here you can easily write kBt by m, kBt by m into minus e to the power minus t by tau v divided by 1 by tau v, 0 to infinity. For infinity it will be 0, for 0 it will be 1, but there is minus, so minus minus cancels out, so it becomes kBt by m into tau v. Okay, so think about this logic. So what we have done here, we are integrating for t1, but this t1 is very very greater than tau v. That means if it is very very greater than tau v, then we can replace this constant tau t1 as infinity, because we are doing with respect to tau v, means tau v is the time scale, important time scale here. So we have just changing the integration limit to infinity, and from that it is just follows easily from there. Okay. Okay, so now let me also, if you do this, then you can easily write then d is equal to kBt by m, and tau v is m by gamma. M cancels out and it becomes kBt by gamma. So this famous thing is called Einstein relation. So this is called D is equal to kBT by gamma is equal to kBT by 6 pi eta a. So this is called famous Einstein relations. So equation 35 is called Einstein relation. And this Einstein relation is also a fluctuation-dissipation relations. Okay, so some notes. Einstein's relation is another example of fluctuation dissipation relation. So in what sense? Because D captures the fluctuation of the particle positions, right? Because it's changing its position, that's why it's diffusing. So in this case, the fluctuation of particle positions, the fluctuation of particle position which is represented by diffusion constant, self diffusion constant D, is related to the dissipative force, is related to frictional constant gamma. Now we will, in the later stage, we will establish the general form of fluctuation dissipation relation. Okay. Now one more thing. We have made a certain assumption earlier. We have made the assumption that T is very greater than tau v. Right. Now these assumptions is usually satisfied in soft matter systems because there the observation time scale is around millisecond, right? And this assumption is usually satisfied in soft matter systems. Okay. So because the velocity correlation time tau v is very short compared to the time scale of soft matter. Okay. So to understand this from an example point of view, so let's say a colloid, uh, typical colloid suspended in a fluid, let's say water. So it has a radius, let's say a is equal to 0.1 micrometer. So for that, if you calculate the tau v, this will come about 10 nanosecond, while the characteristic relaxation time of relaxation time of colloid particles is of the order of millisecond. That's why in the previous descriptions we assumed that IV tau v. So in the earlier discussions, we assumed tau v is very small. Okay. Now since it's infinitesimally small, or you can write as infinitesimally small. Now in that limit we can easily write Vt prime as 2d delta t minus t prime. So in that limit we can easily write this relation, and this coefficient must be equal to 2d by relation of this thing. Okay. So the coefficient of the delta function must be this, so that we can get the same value. Okay, so before doing that, let me do the calculations again. So before I think we have to do the calculation for the general case, the displacements. So calculation of MSD, okay, for general case. Okay, so we will use this relation, okay, 19 probably. We will use this relation, okay. So from this relation we will try to get to see that how it will going to be changed. Okay, so okay, so what should we do? So basically what we'll do here, we'll calculate the equation. So okay, so basically the equation is m dv dt is equal to minus gamma v plus fr t. Now if you solve it, you get v of t is v0 e to the power minus e to the power minus t by tau v plus 1 by m 0 to t dt. Let's say this is dt1 and dt1 and e to the power minus t minus t1 by tau v fr t1. Okay, clear, right? So if you get this quantity to be 0, since it is exponentially falling off, so then from this point of view you are only getting, similarly Vt prime is V0 to the power minus T prime by Tv plus 1 by m 0 to T prime dt2 to the power minus T prime T2 by tau v fr tt2. Now if you take the average of v of t, then only this term survives, because average of fr t1, that is 0, that is also for fr t2, same thing, right? So if you do that, then only thing that remains vt2, vt and vt prime is v0 square e to the power minus t plus t prime by tau v plus 1 by m squared minus infinity this will be minus infinity, this will be minus infinity, sorry, minus infinity to t dt1 minus infinity to t prime dt2. Okay, so now it remains to be seen that e to the power becomes minus t minus t1 by tau v times minus t minus t2 by tau v into fr t1 and fr t2, these two things. Okay, so that we need to do. So okay, so now you can get the cross term from these two things will be going out, right? So the mean square velocity that remains is this. Now if you just replace t prime by 0 by just 0, then you can get some interesting thing, because then you have to just take the square of this, right? If you just do these things, let's say if you want to calculate only v of t whole squared, then that only comes to be v0 squared e to the power minus 2 t by tau v plus 1 by m squared, 1 by m squared. Now we can do the whole thing as minus infinity to t dt1, similarly minus infinity to t dt2, because these things are same, and e to the power minus 2t by tau v into e to the power t1 plus t2 by tau v, and the average of fr t1 and fr t2. Clear? Right. So in that scenario, what you are getting is this will be a certain thing. Let's say this is 2 gamma kbt delta t1 minus t2 in these relations, or we replace it by some constant, let's say a. So then it becomes v0 whole square e to the power minus 2t by tau v plus e to the power minus 2t by tau v divided by m squared minus infinity to t dt1, and this minus infinity to t dt2 a dot delta t1 minus t2, this becomes to be, so this a becomes a and this is 1, so v0 whole square e to the power minus 2t by tau v, and here it remains T1 T2, this will be T1 plus T2 by tau v. Yes. So then for this part we will do first. So this is e to the power minus 2t by tau v by m squared, and this is now what this is a sum. These integrations will be can be by this integration can be done in two ways. Let's say this is two variables, t1 is varying in this way, t2 is varying in this way, and they both are varying from 0 to t, 0 to t. So since t1 t2 varies like this, and this is t1 by t2 curve, so what we can do, we can get that let's say t1 is less than t2. So t1 is less than t2 always in this region, right? In this region t1, let's say this point, t1 is greater than always t2, right? So in this region t1 is greater than t2, so we will take only this part, then it becomes minus infinity to t. Since t1 is greater than, so this t1 will be like this, so and this will be minus infinity to t and d22, and this integration will be done, and so you can get that there will be 2 times this. So we will be getting by 2, and here the limit of t2 will be always t1, so this will be t1. So if you do that, then this integration becomes dt2a 2 times because of these relations, and delta t1 minus t2 times e to the power t1 plus t2 by tau v. So then it becomes into two part. So the minus infinity part will be the 0, the 1 will be only there, so we can suppress this part to keep it as 0. So this becomes v0 square to the power minus 2t by tau v plus 2 into e to the power minus 2t by tau v by m squared 0 to t dt1, since this is 0.21, so this becomes e to the power 2t1 by tau v into a, and after this integration this becomes v0 square to the power minus 2t by tau v plus 2 into e to the power minus 2t by tau v by m squared, and this relations becomes e to the power 2t1 by tau v but by 2 by tau v 0 to t, okay, 0 to t, and then v0 square e to the power minus 2t by tau v plus, for 0 it will be 1, so 2 e to the power minus 2t by tau v into tau v by 2 by m squared into e to the power 2t by tau v minus 1. So from there you can easily write to the power minus 2t by tau v plus 2 cancels out, and it becomes, and there will be 1a also there and 1a there, so a tv by m squared into 1 minus 1 minus to the power minus 2t by tau. Now this part A is 2 gamma kbt, so you can write 2 gamma kbt into tau v is m by gamma by m squared. From there you can easily get 2 kbt by m, or you can get 2d. So this will be around 2d, and if you take this will be 0, this will be 2d. So now you can easily write bt squared. So kbt by m is not 2d. Sorry. So this is not 2d. So this is this thing. So in the next step we have to do the calculations to get the mean square displacement calculations. Okay, so we'll stop here and we'll discuss the next topic in the next class. Okay.